All right, so in this lesson, we're going to take a look at Taylor polynomials and try to come up with a general formula that can be used for many different functions. And we're going to do this by looking at a few examples here. So in this one, what we are starting with is two different functions. We have an f function, and we're going to look at a g function and do them one at a time. Starting with the f function, we know that f of 0 is equal to 5, and we know that f prime of 0 is equal to negative 3. This is really our linear approximation, or finding the equation of a tangent line that we have done many times throughout the year. And so in this situation, you would just simply use your slope or point slope form, which would be y minus y1, which is 5, equals m, which is your slope or derivative, and that is negative 3, times x minus x1, which is 0. And then if we were to distribute here, we end up with negative 3x, and y would equal 5 minus 3x. And I did put it in this particular order for a reason that we'll see a little bit later on. So in the next function, we know that g of 2 is negative 4. So we're going to have y minus negative 4 is equal to the derivative, which is 1/3, times x minus, and then 2. And so distributing, you're going to have y plus 4 is equal to 1/3. And I'm going to actually leave it in this format and then just move the 4 over, giving us negative 4 plus 1/3 times x minus 2. And I'm going to leave it in that format because we're going to see why in a little bit later on. So in this situation, if we let f of x equal some generic quadratic, you would have a constant function, another constant times x, and another constant times x squared. Now in this situation, that means that f prime of x, well, the derivative of c sub 0, derivative constant is 0, so we're going to be left with c sub 1 plus 2c sub 2 times x. And f double prime would equal 2c sub 2. Now, if we were to evaluate at our x value of 0 as we have here, then that means that f of 0 would equal c sub 0 plus c sub 1 times 0 plus c sub 2 times 0 squared, which is 0, which is going to give us c sub 0. And since f of 0 is 3, that means c sub 0 would equal 3. Now, f prime of 0 would equal c sub 1 plus 2c sub 2 times 0, which would give us c sub 1. And since f prime of 0 is equal to negative 2, that means c sub 1 is equal to negative 2. And then f double prime of 0 would equal 2c sub 2. And since f double prime of 0 is negative 4, that means c sub 2 is equal to negative 2. All right, so we can piece together our function now And so that would end up giving us then f of x is equal to c sub 0, which we found was 3, plus c sub 1, which was negative 2. So I'm going to write this as minus 2x, plus c sub 2x squared. So that would be minus 2x squared. So we were able to build our polynomial based upon a few things. We were given what the function at 0 was, the derivative at 0, and the second derivative at 0. By knowing these three things, we were able to put together a quadratic equation at that that satisfies that information. All right, so let's try this again with another problem here. Find a quadratic function such that g of negative 3 is 4, g prime of negative 3 is 0, and g double prime of negative 3 is 6. All right, so this situation is a little bit different because we have a g of negative 3 instead of a g of 0. Now, the way that's going to change things is our function is going to be written as c sub 0 plus c sub 1 times x plus 3. And if you go back to your linear functions and think what we had on the other page, on the linear functions it was x minus x sub 1. Well, in this situation, our x sub 1 is going to be negative 3. And so instead of x in our problems that we had here and here, what we're going to have is going to be an x plus 3 instead of just an x. And so finishing out our generic equation here is going to be plus c sub 2 times x plus 3 squared. So that's our general quadratic. And so what we want to look at then is what is g prime, which would be c sub 1 plus 2c sub 2 times x plus 3 to the first power. And then the second derivative at x would equal 2c sub 2. Now, if we evaluate each of these at negative 3, that means g of negative 3 would equal c sub 0 plus c sub 1 times x, let me replace x with negative 3 plus c sub 2 times negative 3 plus 3 squared. All right, so what happens then is this is going to be 0, so this whole term is 0. Same thing here, so this whole term is 0. And that is going to leave us with g of negative 3 is equal to c sub 0. And g of negative 3, we know from above, is 4. So therefore, c sub 0 is equal to 4. All right, so let's carry this on now. G prime of negative 3. We move to the derivative function right here. And that's going to equal c sub 1 plus 2c sub 2 times negative 3 plus 3, which this term is going to go to 0, leaving us with g prime of negative 3 is equal to just c sub 1, and g prime of negative 3 was 0. So therefore, c sub 1 is 0. And finishing out the second derivative here at -3 is just 2c sub 2. There is no x value to substitute the -3 in. And we knew from above the second derivative is equal to 6, which means c sub 2 is equal to 3. And we can piece this all together for our equation. So g of x would equal c sub 0, or sorry, yeah, c sub 0, which we found was 4, plus c sub 1 times x plus 3, but we found c sub 1 was 0, so that's going to actually take this term out of the picture, because 0 times this will be 0. All right, so now we have plus c sub 2, which we found was 3. So we're going to have 3 times x plus 3 squared. All right, so the next one says find a quadratic function such that f of 2 is equal to 8, f prime of 2 is equal to -1, and f of the second derivative of 2 is 3. All right, so what I want you to do is pause the video and work this problem out, and then unpause and see if you have the same result. All right, welcome back. And so as you can see, here's your work. I shortened it a little bit. We found the value of c sub 0 is 8, c sub 1 is -1, and c sub 2 is 3/2. And then substituting those values into our general form here, we end up with f of x is equal to 8 minus x minus 2 plus 3/2 times x minus 2 squared. All right, so the next one is just a little bit different. It's asking us to find a cubic function. And again, it's giving us this information. Notice that instead of just giving us the second derivative, we are now given the third derivative so that we can find the c sub 3 value. So follow the patterns with what we have been doing. I want you to pause the video, take a few minutes to work the problem out, and then unpause the video and see where you are with your results. All right, so you can follow the work that we have used here, this being our generic form for a cubic. And we found the first, second, and third derivatives and set those equal to the values that were given to find c sub 1, 2, 3, and substituting them into our generic formula right here. We end up with f of x is -1 plus 5x plus 1/10 x squared minus 2x cubed. So here is a more formal form for f of x for a cubic, and where the constants are unknown numbers that we need to find the values of. And that's exactly what we did on the other page. Now, one of the things to notice here is that when you bring this exponent to the front, it really becomes a 2 times a 1, because there's an understood 1 right here. And 2 times 1 is the same thing as 2 factorial. And so that's what we end up with here is a 2 factorial. When we bring this exponent to the front, it becomes a 3. And then when we do the next derivative, we bring this 2 to the front, giving us 3 times 2 times 1. Well, 3 times 2 times 1 is really 3 factorial. And that's where this comes from right here. So instead of writing a 6, I wrote it as a 3 factorial. Instead of writing it as a 2, I wrote it as 2 factorial. All right. So once again, I want you to take just a few minutes to work through this problem. Pause the video, and then in a few minutes, unpause it and compare your result to the actual answer. All right, go ahead and take a second to look at this. What we came out with in this situation was that c sub 0 was 0. And what that means in the long run is that this term gets dropped off of our answer here. And so we start with c sub 1 times x minus 1, where c sub 1 was 4. And that ends up being our first term for our polynomial. Here, I went ahead and left it as 2 factorial and 3 factorial on these, and gives us these two values that we substitute in to give us this polynomial. All right, so let's work one more, and this time we're going up one more step to a quartic function. So once again, follow the same procedures that we have done on the other slides. Take a few minutes to work this out for yourself, and I want you to pause the video right now, and then when you're done, unpause the video, and you can compare your answer to the answer that we have here on the slide. All right, so as you can work your way through the problem, you can find out down here that c sub 0 is 3, c sub 1 is 0, c sub 2 is this, and c sub 3 and 4 are these values here. Now, because c sub 1 is 0, that means that this term is going to go away. So we're going to go from the constant to the term that has a second degree here. So we have the constant is 3, and then we have the term that's raised to the second power. All right, so a couple of things to notice. If you'll notice the exponent here, the exponent is 2, and you have a 2 factorial down here. The exponent is a 3, and you have a 3 factorial down here. Exponent is 4, and you have a 4 factorial. That is your pattern on this. Here the exponent is 0, which means this is over 0 factorial, which is 1. So even though you don't see it, it's still the same pattern that falls in with that. All right. Then the other thing to notice, this is your derivative evaluated at -1. So this is your second derivative. Exponent's the same, so it's this derivative. This was your third derivative evaluated at -1. This was your fourth derivative evaluated at -1. So these numbers all work together here. All right, so the next thing we can do is we can look at a generic formula for a third degree Maclaurin polynomial for f of x equals e to the x. All right, so if we use the system that we have been doing thus far, here f of x would equal c sub 0 plus c sub 1 x plus c sub 2 x squared plus c sub 3x cubed. The next one would be the first derivative, and that would be c sub 1 plus 2c sub 2 x, and this is 2 factorial, remember, plus 3 times c sub 3 x squared. The next derivative would be 2 factorial c sub 2 plus, now we're bringing the exponent of 2 down with the 3, so that makes it 3 times 2 times 1, which is 3 factorial, times c sub 3 x, and then next derivative is just 3 factorial c sub 3. And evaluating each of these, c sub 0, well, e to the 0 is 1. F prime, well, the derivative is going to be e to the x. All of these derivatives are e to the x. So this is going to be 1. And then putting 0 in, you end up with this equals 0, therefore equals 1. Therefore, c sub 2 is equal to 1 over 2 factorial. And then the last one ends up being 1 over 3 factorial. So what that gives us then is a polynomial starting with c sub 0 is 1 plus 1 multiplied by x, so we have just simply x, plus 1 over 2 factorial, x to the second power, plus 1 over 3 factorial, x to the third power. And that is your generic formula for a third degree Maclaurin polynomial for e to the x. All right. And down here we can take a look at how this polynomial compares to the actual function e to the x. Here, e to the x, that is the red graph, and the polynomial, the Taylor polynomial, is your blue graph. And you can see that the blue graph really is a pretty good approximation between here and here. It's a pretty close approximation. And at x equals 0, you actually have a perfect approximation. It's not an approximation anymore. It is a perfect value. Okay, and so here you can see how the values compare. At x equals 0, it's perfect. As you move away from x equals 0 to the left and to the right, here you can compare the numbers: 349, 0.349, 0.816, 0.822. So the further we get away from this x equals 0, the less accurate our approximations are. However, they are still pretty close. They're accurate to the tenths place anyways. And it does the same thing going this direction. Close to 0, they're pretty close in approximation. And then the further away we get, it starts to deviate just a little bit, even though it's still a really good approximation at this value here. Okay. So if f of x is differentiable in times at x equals a, then its nth order Taylor polynomial centered at a is given by this polynomial right here. You have f of a over 0 factorial. Remember, 0 factorial is 1. And so it's just your function evaluated at a. This is your first derivative over 1 factorial. So it just ends up being your first derivative times x minus a. Second derivative at a over 2 factorial times x minus a. And that pattern continues on, giving us a general form for the each term being the nth derivative evaluated at a over n factorial times x minus a raised to the n power, which can be written like this as well using sigma notation. Now, if a is equal to 0, then that means that our function is centered at 0, or Taylor polynomial is centered at 0, and we can call it a Maclaurin polynomial. So what we want to do now is we want to find the third degree Taylor polynomial centered at x equals 2 pi over 3 for f of x equals sine of x, using that formula instead of the long procedure that we did on the earlier part of the video. All right, so third degree, that means we're going to have to find the third derivative. All right, so let's go ahead and work at finding this information. We know that f of x is equal to sine x. We know that f prime is equal to cosine. The second derivative is equal to negative sine. And the third derivative is equal to negative cosine. Now from this we can do some values at 2 pi over 3. All right, so the sine of 2 pi over 3, that is equal to root 3 over 2. Cosine of 2 pi over 3 is equal to negative 1/2. Sine of 2 pi over 3, we already said was root 3 over 2, but we've got a negative in front, so that means this is equal to negative root 3 over 2. And the third derivative would be cosine of 2 pi over 3, that's negative 1/2, but again we've got a negative in front, so that turns it into a positive 1/2. All right, so we can piece together our polynomial from this now. So that gives us our polynomial is going to be f of x. Now let me go ahead and use the notation that we would use for a Taylor polynomial, and that is p sub 3 of x is equal to the function evaluated at 2 pi over 3, and that's going to be root 3 over 2, minus your first derivative, which is 1/2 over 1 factorial, centered at 2 pi over 3, so we're going to have x minus 2 pi over 3 to the first power, minus root 3 over 2 over 2 factorial times x minus 2 pi over 3 raised to the second power, and then we have plus 1/2 over 3 factorial times x minus 2 pi over 3 raised to the third power. Now this could be simplified just a little bit, giving us root 3 over 2 minus 1/2 x minus 2 pi over 3 minus root 3 over 2 times 2 factorial plus 1 over 2 times 3 factorial times x minus 2 pi over 3 raised to the third power. All right, so now you're being asked to find a fifth degree Taylor polynomial centered at 3 pi over 2 for f of x is equal to cosine of x. Use the method we did on the previous problem to find this. I want you to pause the video, work the problem out, look back at the previous problem to help yourself, and then unpause the video and when you're done, and check your answer against what you will see here. All right, so since we're finding a fifth degree Taylor polynomial, we needed to find the fifth derivative, and it just kind of bounces back and forth between cosine and sine and positives and negatives. And then evaluating at 3 pi over 2, because that's where we're centered at, that gives us these particular values here. Now notice that we've got zeros here, here, and here, which means that the function, the first term, goes away, and we end up with a first term having an x on it. The second derivative term goes away, and the fourth derivative term goes away, which means we're not going to have a term that has a second degree or a fourth degree on it. Now, these are Taylor polynomials that you must memorize for the AP exam. You do need to memorize your Taylor polynomial for e to the x, cosine of x, sine of x, and 1 over 1 minus x, because we can use these four functions to find Taylor polynomials for an infinite number of functions, where we can substitute something in for x, or we can multiply by a constant, or many different things here.